This is the Decision 2 paper from 2022. First question then is about the Hungarian algorithm. So we start with this. We're going to reduce rows first. So we find the smallest element in each row, so 32, and remove it from the entire top row. So just take 32 away from all these. Then take 37 away from all those. Then take 40 away from all of those. Take 43 away from all those, and we end up with this. And then we do the same thing with the columns. So the smallest column or smallest entry here is 0, so take 0 away from all of these, you just get the same thing. Take 2 away from all of those, you get this. Take 0 away from all of those, and then take 2 away from all of those. This ends up being your nice reduced table here, which you can now use. Cover up all the zeros in as few lines as possible. I think we can do it in 3, like this. Now, it's a 4x4 table, so optimal solutions are found when we can cover up all the zeros with 4 lines, not 3. So what we need to do is look for the smallest uncovered element, which is this 2 here. And what we'll do is we'll remove 2 from all of the uncovered elements. We'll leave the ones covered by 1 line alone, and we'll add 2 to the double covered ones. So this becomes an 8, this becomes a 4, and all of these are increased by 2, and we end up with this. I think, all of these are decreased by 2. These ones are increased by 2, these ones are decreased by 2. I think I said that, so cool. And now, can we cover up all these zeros with less than 4 lines? I don't think so. I think this is a 4-line job. No matter how you do it, I think that's a 4-line job, which means this is optimal. And so now we just need to place A, B, C, and D in the right place with all the zeros. So, okay, well, the only 0 in row 4 is C, so C should be doing job 4. If C is doing job 4, then the only 0 left in 3 is A, so A should be doing job 3. And then B and D, actually, you can get to do either one. You can get either B to do 1 and D to do 2, or B to do 2 and D to do 1. They would both be optimal. And when you're looking at the total minimum cost, so okay, C does 4, that's 42. A does 3, that's 34. And then B does 1, in my case, that's 37. And then D does 2, which is 45. But you can notice 37 and 45 add up to the same thing as 39 and 43. So we end up with this as our total job cost. And that will be good. We're done with the first question. Second question is a thing about recurrence relations. So this is already in homogeneous form, so we can just get the auxiliary equation m squared plus k1m plus k2 equals 0. We can solve this, except this here implies that the solution is repeated because of the a plus bn form, and also this is the solution here. So this quadratic here must factorize to be the form m plus 3 all squared, because this gives us a repeated solution at minus 3, which would be this here. So okay, if we just expand that out, we get this, and then we can say k1 must be 6 and k2 must be 9, and we'll have our answer. Given u0 is 1, well, if u0 is 1, put in 0 here, we get 1 as this. B goes away because b times 0 is 0, and this just becomes a minus 3 to the 0, which is 1, so we just get 1 equals a, and that's good. If we put n is 1 into here, we get u1, which is also 1, equals a, which we know to be 1, plus b times 1, which is just b, times minus 3 to the power 1. So we get this, and that's just, this line is just replacing a with 1, and then we put n is 1 in, and we get this. And divide by minus 3, and take away 1 or whatever you want to do, and we get b as that, and that will be the second question done. Question number 3, then, is one of these things about a decision tree. So the tree starts with a rectangle, then you do circles, then you do triangles. So car, train, coach is how I've spelt this out, and we'll fill this first one in slowly. So usual travel time happens with probability, we'll do 1 minus this for 0.88. So usual travel time happens with probability 0.88, and causes a total time of 52. And then probability of this sort of delay is 0.1, and delay time is 10, so add that onto this time and you get total time of 62. And then likewise 0.02, add these on, you get 77. And so that's the tree for this top bit. I'll just fill in these two bits exactly the same. You can verify what I've done there. I'm just doing exactly the same idea. So this 0.92 comes from 1 minus this, and that has 45. And then you add 15 for this one, add 25 for this one, put these there, and so on. And then this circle here is gotten by doing this times this, plus this times this, plus this times this. Putting that in the calculator, you get this. So that's the expected time for the car. For the train, you do this times this, plus this times this, plus this times this. You get that, that's for the train, and then lastly for the coach, and you're picking the smallest, of course, which will be the train at 46.5 minutes. Good. Question number 4 then is one of these capacity things with the circle is how much is actually going through it, and the just the regular number is the maximum amount that could go through it. They've been really annoying and swapped the order of them, so you actually have to look at the circles, but I don't know whether they always do that or not. List the saturated arcs, that's the ones that have the amount going through the most they could have, or just essentially where the two numbers match. So A to E, S to B. Look in the table super closely. You don't want to throw a mark by missing one, so just look in the table super closely for every number matches. State the value of the initial flow is these three circled numbers added together initially. So that's the actual amount. I think of this as water flowing through pipes. The actual amount of water that's leaving this source here is this plus this plus this. We get that. Explain why FT cannot be full to capacity. Well, FT is this one. Currently you can see it's not full. It's 5 short. But look at the two things coming into it. At most, 14 plus 8 could be coming into it. That's 22. So it could never be full because its max is 24. So even if these two were saturated, you couldn't have this actually be saturated at all because those are the only two going into it. State the capacity of C1, so that's just you add up the non-circled numbers that are actually going through C1 in this direction. So in this case, 33 plus 41 plus 30, and we get this. And then for C2, it will be 53 plus 30 plus 14. This one's going the wrong way, so we don't add that. And then 17, I've just put a plus 0 just to denote that this one I don't add in. I essentially add in 0 if you like. And we get that. By inspection, find an augmenting route to increase the thing by 3 units. So okay, we could increase this by 3 units. That would be fairly logical. That would make it up to 32. That's fine. We could then increase, we can't do anything with this. We could increase this by 3 units to get it to 12. That's good. But then we look around B, that's saturated, saturated, saturated. So how do we make any more progress? Well, what you could do is you could reduce this by 3 units. Like if you've increased this and this by 3 units, you've got 3 more units flowing into B. If you reduce this by 3, then that works. B will have the same amount coming into it in total. So we increase by 3, decrease by 3. But of course, if this is decreased by 3, the 15 going into here with the 3 leaving it, these two need to be increased by 3. But that's fine, because I can increase that by 3. So just to run through that, this one's been decreased by 3, so there's 3 less flowing out of D. So I need to balance that, I need to put 3 more in here, and then of course I can put 3 more in here, and that'll be my route. So S to A, A to B, decrease that, B to D, increase, and we'll have our route. Prove that once we've done that, this flow is maximal. Well, the flow now, it's been increased by 3, it was 95, I think, so it's now 98. And we just need to find a cut. This is the maximal cut, minimal flow idea. We just need to find a cut. We just need to find a cut that's 98. And you can look around it. You've got a calculator, so you just keep making cuts until you find something. 20 plus 22 plus 30 plus 14 plus 8 plus 4, if I call that C3, is 98. So by the maximum flow minimum cut theorem, we have that these two things, that this must be maximal because of this theorem here. And we're done. Good. Question 5 then. So this is one of those questions where we have to set up some stuff and some tables. It sounds good. So we've got all this jargon here. Essentially what this is saying is it costs 23 to transport something from A to R. And it costs 17 to transport something from A to S, and 24 to transport something from A to T. Now, given the problem is balanced, state the value of K, so K is down here somewhere. So these things here, this is saying here how much you can take from supply A, or from like factory A. You can take, and you can distribute it out to all the other places, but you can only take up to 34, that's how much it's got. And factory B has 27, and C has 41, and so on. And then when you get to these signs, that means that R, which is like the place you're going to, so we can imagine these as maybe the stations that need whatever it is that they need. R needs 44, and S needs 37. And if this is a balanced problem, T needs K, the amount we can get, the supply we can get, is equal to the demand. So therefore, these 4 added together are equal to these 3 added together, and we'll get K as 39. Explain precisely what this means. See, I think I just said that, right? So this means that whatever we're calling R, so like the warehouse R, let's call it, if these are warehouses, requires 44 from all of the sources it can get it from. So we need to transport 44 units to R at some point, at least. Like we could do more if you wanted to, although it probably won't be optimal. But all of the combined sources here need to combine to get 44 into R at least. use the northwest corridor thing. So we've got the table here. We'll start here. So we've already said that that A can give out 34. So let's just give out all 34 to R. Now R needs 44, so that's fine. There'll be 10 left over. So let's go downwards, and we'll say we're done with A because A has given all it can give. So we'll put the extra 10 that we need to fill up R. We'll give that drop to B, and B can give out 27, so it's got 17 left. So we'll just put all of those there. And then, of course, we've run out now, so S needs another, 20? So we'll take that from C. C can give 41, so that has 21 left over, which we'll give to T. And T requires, we said 39, so it needs 18 more, which is perfect, because D can give us exactly 18, and this will be our initial thing. And then we also need the cost, though, so we'll do 34 times the cost to go from A to R, which is 23, as I said earlier. So 34 times 23, plus 10 times B to R, which is 15, plus 17 times B to S, which is 29, and so on, and we'll get an initial cost of this. Perform an iteration of the stepping stone. So what we'll do, if I just cut this up a little bit to get me some space, this is the cost matrix. I could have drawn this earlier, couldn't I? It would have probably helped us to see what was going on, but this is the sort of the cost that it takes to transport things from one place to another, and this is how much I'm actually transporting. So let's do some shadow costs then. So let's just do the cost matrix, but let's ignore the places we're not currently using. Start with a 0 here, and then of course this number plus this number, the shadow cost must add up to this. So put a 23 here. Of course, if this plus this makes 15, then this is minus 8. If this plus this is 29, then that's a 37. If this plus this is 25, then that's a minus 12. This plus this here is 27, so that's a 39. And then finally, this makes a minus 14 all the way down there. And now what we do is we fill in the rest of the column by doing, so for example, this box is going to be this, minus this, minus this. So 25 minus 23 is 2, minus 12 is 14. And then 19 minus 23 is minus 4, minus 14 is 18. And then here, 17 minus 37 minus 20 minus 0 is minus 20, and so on. And you fill up all those like that. And then you look for the most minimal, which is this one. So what's that saying is that's the one we can save the most money if we actually use. So what we do is we open up this table and we say, okay, I want to put some units here. I'll just call them theta. Now, if I put theta units here, then this one needs to decrease by theta, because A can only give 34 units. So if you put theta here, you need to take them away from here. But of course, if I've taken them away from here, R still needs 44, so we'll have to add in theta here to make this still balanced to make 44. And then of course we need to take them away here. And actually, I think that's balanced now. This column is good, this column is good, this row is good, this row is good. So now we'll just bang in the other three, and we'll have this. And now we don't want to make any of this negative because we can't transport negative goods. So the most we can make theta is 17. So we'll just choose theta to be 17, and that makes this 0, this 17, this 17, this 27, I believe. And now we'll just, actually, I don't think we even need to figure out the cost. I don't think it even told us. I think I did figure out the cost and then deleted the thing because I realized I didn't actually need it. I shouldn't have deleted it, I should have just kept it. But anyway, this is now the solution after one iteration. And the exiting cell is BS, because that one's gone away. And the entering cell is AS, because that one's been entered in. And we'll have that as our answer, I think. Question 6. Now, this took, I think, maybe an hour to type into PowerPoint. Jesus Christ. So we've got to fill in, this isn't even everything that I'll fill in. Once I filled in this entire thing, I'm going to move it over here and fill in some more. So, okay, let's go through this. I mean, what I will say is, if you have this question under wraps, if you understand what I'm about to do, when you do your paper, you can pick up an immense amount of marks if it comes up, because none of this is going to be hard. It's going to be super repetitive. If you can just get your head around it, there's a lot of marks maybe to pick up here. So, okay, what's going on here? He makes sheds, right? He can build up to 4 sheds a month. If he builds more than 2, he has to hire an extra guy. We'll call this guy, what should we call this guy? Steve. We'll call Steve in. So Steve will come help us if he needs to buy an extra one, if he needs to build more than 2. If he builds a shed, it costs 35 per shed. And a maximum of 3 sheds can be stored at the end of a month at a cost of 80 per shed. And he must deliver the sheds out. There are none in storage to start with, and he wants to have none in storage after May. Maybe he's going on holiday or whatever, and he's not going to work after May. Now, this is dynamic programming, so we're going to start at the end. We're going to start at May. So they filled this in to start with. What they've said is, state is the number of sheds in storage before this month. So state 2 means entering May, there are 2 sheds in storage, which means he doesn't have to build any. Action is how many you build. He doesn't have to build any because he's already got 2 in storage. He only needs to give 2 out, and he doesn't want to have any in storage afterwards, and that's destination is how many in storage afterwards. So okay, he's got 2 in storage, he doesn't need to build any, he's got none afterwards. He therefore only has the cost of 160 because that's the amount that it costs to put a shed in storage, and he's got 2 of them there, so that's cost of 160. If he's only got 1 shed in storage entering May, then he needs to build 1 to get to 2, and therefore he won't have any left over, which is good, and that's the cost of having it in storage, that's the cost of building 1, and we have this cost here. If he's got none in storage entering May, he has to build 2, which costs 70, and we have this 70 here. Then we go backwards, we go to April, and we say, okay, what if he's got 3 in storage heading into April? Now, he needs to deliver 5, so he's going to need to build minimum 2. If he builds 2, he'll have none in storage afterwards, and that's fine. He could also just build 3, because he can build up for 4, right? Or he could build 4. If he builds 2, he'll have none in storage afterwards, because he needs to use all 5, the 3 in storage and the 2 he's built. If he builds 3, he'll have 3 in storage, built 3, 5 are on order, so he'll have 1 in storage, which will go up to May, right? And this will be this row we'll use. And then if he builds 4, he'll have 2 in storage. Now, how much does this cost here? Well, he's got 3 in storage, that's 80 times 3 is 240. He builds 2, that costs 70, because each costs 35. And then, so it costs him 240 for storage, 70 to build, and then working backwards, if he's got 0 in storage, then we would then use this cost here of 70 for our final total. So we're going to add in these starred amounts to get our running total as we go downwards. So we'll add in this 70, say, if he does this, the final cost in the next month will be an extra 70 here, and we'll add that in as well to get 380. Then here, if he builds 3, that'll cost him 105, plus he has to hire in Steve, remember? He also has to pay for 3 sheds to be in storage, so that's 240. And he also has to pay 115, because that's the cost it will take in May if he enters May with 1 in storage. And we get this cost. If he builds 4, that costs 240 to put these in storage. It costs 140 to build 4, he has to hire in Steve, and it costs 160 to deal with May if he has 2 in storage to start with. And that costs that. Now, the most optimum solution here is this 380. So what we're saying here is, if he enters April with 3 in storage, the most optimum thing to do is to build 2, have none in storage, and that will cost a total of 380 once you account for May as well. And we'll basically ignore these 2 rows from evermore, because when we do like March, we'll take this value, that's why it's got a star next to it, we'll take this value if we're ever looking at going into April with 3 in storage. But okay, we could go into April with 2 in storage, in which case we'd have to build a minimum of 3 to get up to 5, and we'd have none in storage, or we could build 4, in which case we'd have 1 in storage. Building 3, well, having 2 in storage costs 160, building 3 costs 105, and you have to hire in Steve, and going into May with none in storage is a cost of 70, and so we get this cost here. Building 4, you keep 2 in storage is 160, building 4 is 140, you have to hire in Steve, and £115 are spent to get through May if you've got 1 in storage, so you get this cost. And the best way of doing that, this is the cheapest one, and so therefore if you enter April with 2 in storage, this is the price we'll go with from then on. If you enter April with 1 in storage, you have to build 4, because you need 5 by the end of April. Obviously none will be in storage. It will be £80 to keep that in storage, 140 to build those 4, you have to hire in Steve to help you, and it will cost 70 to do May with none in storage, and it will cost that much in total. So then we go into March. You can't enter April, you can't do April with none in storage because you can't build 5. So we go to March next, and we say, okay, what happens if you enter March with 3 in storage? Well, you could build 0, because then you have 3 of them, and that will leave 0 as your destination, except actually this can't work, right? Because you can't enter April with 0 in storage. So this row is actually bogus. We have to build at least 1, even if we've already got 3, because we have to have at least 1 in storage to enter April with. We can't enter April with none in storage. So we do this, or we could build 2, we could leave 2 in storage, we could build 3, we could leave 3 in storage, or 4 and leave 4 in storage. Any of those options are available. Sorry, there aren't. We can't build 4 because we can't put 4 in storage. We can only put at most 3. It does say somewhere here that you can only put 3, there it is, you can only put 3 in storage, so we can't build 4 this month. Anyway, we do our costs. I'm not going to go over this as much detail anymore. You find the most efficient cost for this amount entering March. then you enter March with 2 instead, and you write down how many you could do each time. Why haven't I not built? I could have built 1 surely in March. So you enter March with 1. Oh, but you can't build 1 because then you'd have none in storage, and you can't enter April with 9 in storage. So you have to build at least 2. That leaves 1 in storage. You have this cost and so on. So I won't go through this in as much detail. The most efficient one is this. So I think I've talked through this enough now. So I'll probably just open this up. I'll probably keep talking when we hit February. So we've got all of our most efficient costs for the different. So if we enter March with 3, this is our most efficient cost. If we enter March with 2, this is our most efficient cost. If we enter March with 1, this is our most efficient cost, and 0 is this one. Maybe I should say, actually, going up here, like when we entered March with 3, or sorry, when we leave 2 in storage at the end of March, when we go up here, this is the value that I chose there. I should have made that clear maybe. So if we go back to here, and we'll just go with this row. Having 3 in storage is 3 times 80, which is 240. You're building 2, which costs 70, 2 times this. And then you add 585 because that's the most efficient route from April onwards if you had 2 in storage in April. So that's why we add the 585. And likewise, this one we add 380 because that's the most efficient if you have 3 in storage, not these 2. So that's why we star these, is so that we can find them later and choose the most efficient ones. Anyway, I think I've explained everything that I want to explain. The rest of this is just the same thing over and over again. You keep going backwards. You keep making sure you look at the table and make sure you order in the right amount. You keep starring the most efficient one for each of your states, because those are the ones you want to use later. And eventually, after you do an absolute ton of this and an absolute more of it, you eventually end up going all the way back to January, eventually. Now, January, it should be noted, you don't enter January with any in storage. It said that in the question, but you don't enter January with any in storage at all. So that's why these are all zeros. I could have just done 1 0, I guess, but they're all zeros. And we find the cheapest cost all the way back to the start, which is this. The cheapest cost is this, and the plan is you build 2 in January, and now we have to find this 1080. That involves building 2 in February. Now we have to find this 930. That involves building 4 in March. Now this 540 came from building 4 in April, and that 70 came from building 2 in May. And that will be our entire plan, and that's the 14 marks. Excellent. So question number 7 then is one of these game theory questions. So firstly, we'll find the minimum from each row, which is -2, either -4 or k, depending on which is smaller, and -3. And now, player A wants to minimize their losses. So they'll pick the row that has the largest potential loss. Sorry, the least bad potential loss is probably how I should say it. And the least bad potential loss here is this -2. Now, so that's called play safe. He's going to pick this row because at most he can lose -2. If he picks this row, he might lose -4, and if he picks this row, he might lose 3. But he'll lose. When I say lose -2, I just meant lose 2, didn't I? So he might lose 2 here, but that's the play safe row because he's losing the least. Now, even if k is like -10, that's still worse than this. He's still losing more, and if k is like 100, then he's still losing 4. So in any case, it doesn't matter what k is. You're going to pick this row because you're only losing 2 each time. Given Z is the play safe option B, so let's pick now B. This is the table from A's point of view. So A wins 4 if this happens, and B loses 4. A loses 3 if this happens, and B wins 3. So you kind of need to think of these numbers as -4, 3, 1. If you're looking at it from B's point of view, you just swap all the signs. And then again, you look for the, well, you could look for the least value if you do that, or you could just look for the largest value if you're not bothering to do that in your head. If you're just keeping the table as it is, just look for the largest value, because this 4 represents a loss of 4 for B, and that's the biggest loss here, because this represents a gain, and this represents a gain. So we pick the biggest value, that represents a loss of 6, this is a loss of 3, and this is a loss of whichever is bigger, -2 or k. Now it tells us that Z is the play safe option, so it tells us this is the least big loss, which means that if this is the least big loss, k must be less than or equal to 2. If k was 4, the least big loss would be this. So k must be less than or equal to 2 for this to be the least big loss. Explain why B should never play option X. So we look at option X, and this is one of those dominating questions. So look at option X, he loses 3 here, loses 5 here, loses 6 here. If you look at option Y, he gains 1 there, gains 4, 3 here, and only loses 3 here. So option Y is better no matter what player A plays, right? Option Y is just better for B. Like he wins more here, and he loses less here. So option Y dominates option X because every entry in column Y is better for B than it is in column X. Okay, so what we can do, if a row is dominated or a column is dominated like that, we can just remove it. It's irrelevant to the game because we're assuming that B will never pick it because it's just objectively worse in every case than picking Y. So we'll remove it from the game and we'll reduce our table by not having it in here. Now I've also done something else table, which is that it says here that he's going to add 4 to every entry. So I've removed this column here, and I've also added 4 to all of these entries to make them more positive. It tells you k is bigger than -4, so this is going to be positive as well. So that's all I've done there. It says formulate some constraints here. Now we have that V is going to be less than or equal to. Now if P1 is about player A picking Q. Now and P2 is about player A picking R, and Q3 and P3 is about picking option S. So basically, our winnings are going to be 8 P1 plus 1 P2 plus 3 PS. Sorry, P3, 3 P3 if player B chooses W. Our winnings if player B chooses Y will be 3 P1 times or plus 0 P2 plus 7 P3. And our winnings if Z are this P1, this P2, this P3. So that's set up there. Of course, it's less than or equal to's, so we're going to need to add in some slack variables to make them equal to's, because of course when we're doing simplex, we need to make everything equal to. So I'll add in S1, S2, S3 for slack variables. I've also rearranged all this, because when it goes in the tableau, we just want to read the coefficients like this, don't we? So I've just rearranged it quickly and added in the slacks. And the last thing we need to add in is probability says that all possible options add up to 1. Now, it's very tempting to just write P1 plus P2 plus 3 P3 equals 1, but actually they're they're less than or equal to 1, and we need to add in the slack to make a fourth slack to make them equal to 1. And the reason for that is that we've discounted option X. Although, does that make sense? Because option X is one of player B's options, not one of player A's. So that's interesting. So why does that make sense then? I'm not sure. Let me get back to you on that. I'm just going to keep moving on. We add in a slack. Can I figure this out on the fly? Why did we add in the slack? I mean, I'll tell you the reason I added in the slack is because the number of columns here indicated I needed another one, so I just shoved one in here. And according to the marks team, that was correct. So like initially I just had them equal to 1, and then I noticed this tableau had another column, so I just added in an S4, and then I briefly justified in my head when I was making these slides, because this option is missing, so you've got one less option for them to pick. But at the same time, that doesn't matter, does it? Because that's not part of player A. Player A only has these 3 options, so surely, who cares? So we add in this slack 4 because the table says that we need it. We put down this one, S1, S2, S3, S4, because those are the ones we've added in, and then we just copy in the coefficients. So 1 minus 8 minus 1 minus 1, 1, and then zeros for the other ones, and then value is 0. Likewise here, just don't forget to ignore the zeros if they're missing, like P2 is there. Just keep going, and then of course P is just equal to V, so P minus V equals 0, and that gives us our last one. So that's the tableau filled in. Finally, it says P1 is equal to this, P2 is equal to this, and all the slacks are 0. So if the slack is 0 here, then that means the 3 P's add up to 1, which makes this plus P3 equal to 1, which makes P3 this. And then what I did here was I did this one here, take away this one here, because the V take V goes away. Minus 3 times minus 2 is minus 1 P1. This is 0 P2, minus this is just plus that. Minus 7 minus 1 is minus 6, and then you can just shove in the P1, P2, P3 that you figured out, and you can work out k eventually is equal to 1. And that'll be that question done. Apologies for not being able to come up with a reason for this existing. Maybe I'll write it in the description, or if you know the answer in the comments, just write it in. Otherwise, my justification of needing to fill in the tableau, I think, is a decent enough one. You can just wing it. That's what decision is about, isn't it? It's just about winging stuff. You have a really nice question to do at the very end here that's much easier than the things that we just did. So we have UN represents the company, how many customers you have, and 5,000 the first month means U1 is 5,000, I guess. But it says that it wants you to build up a recurrence relation by saying UN equals P times UN minus 1, which is what this says, plus some value K. So that's just what this says. So UN, the number of customers that in 1 month, equals some proportion P times the previous customers, number of customers that month, plus some constant K of new customers. So that's what that is. And now it wants us to solve this. Now, we just ignore the K to start with, and recurrence relations of this type you should recognize are just given to you as solutions of UN equals some big A times P to the power n. So like if this is UN equals 3, UN minus 1, you have a solution of UN equals some constant 3 to the n. So that's just the solution for this bit, and that's the complementary function. And now we deal with the particular solution, which is we set UN to be some constant lambda, we'll say, and we'll shove that into here. Now UN equals lambda regardless of n. So this becomes lambda equals P lambda, because this is also just lambda, because this isn't dependent on n, plus K. So we end up with this, which we can of course rearrange for lambda. And then we have our general solution of UN equals the complementary function plus the particular solution, which is this. So we get this plus this as our UN. And now using this, we can actually sort of solve for A, right? So if n is 1, this is a 1 here, and we get this is 5,000. And of course we can move that to the other side, divide by P, and we end up with this, and that's our A. And we can put that into there, and we'll end up with this. But of course, this last step of dividing by P, putting these P's here, I could just take those P's out again and reduce that by 1, and I end up with something that might look slightly nicer to some of you. I don't think it's really necessary to do this, but you can leave it like this as well. That's the hardest bit of this question done. Next it says the owner believes 95% of the previous customer's month will be retained. Now that just means that P is 0.95, because that's what P was talking about, is the proportion of the customers that are retained. So P is 0.95, and new customers is 10,000. Well, that's just the K value, is 10,000. And we'll put those two values into this equation here. So just dropping those in, and we want to know when n, which they've now called m, I guess, so there, when that's this, when the number of customers in the month m is this. So I've replaced this with this, and I've just replaced that with an m just because they randomly asked me to do that. And K and P are being put in there. This is just a number, type it in. This is just a number, type it in. Take away that from both sides, divide by this number, the negatives cancel obviously. Do log to base 0.95 of both sides. I've cancelled all the zeros as well. Type that into a calculator, add 1, and you get this. So of course, halfway through the 22nd month, you get these number of customers, which means 23 will be the actual month, I think, that it achieves, that you achieve that. Thank you for watching, and I will see you next time.